and is equal to EI minus d squared W dx squared. So from these two, you can have a minus, you have a EI, the fourth order derivative of W equal to Q. Okay. And or you can have here EI dW dx squared equal to minus m. Minus m. All right, minus m. And EI, the cubic derivative, equal to minus v. Okay, everything you should link together. That's all the Bing equation, so many formulas. You should be very, very familiar with it. Okay, it's very fundamental. Okay, yeah. So always keep it in your mind and very naturally write out. Okay, yeah. And everything based on the definition of this vertical positive Q, downward deflection, horizontal X on this Z. Okay, and with the positive moment definition, vertical shear, and the counterclockwise moment for this X. Okay, X. Yeah. Okay. Positive, you cut at the X cross section is Vx and moment at X. Counterclockwise is positive. Positive. Okay. So this everything being serious. Okay. Now let's talk about the shear strain. So the funny thing is, in the plane section remain plane assumption, this is a cross section, origin normal. Okay. So being after deformation, this AB still have a normal. So that means the no shear strain, right? This conflict, we have a shear stress, shear force. How come we don't have a shear strain? So this is a conflict with the two. So we do have shear stress, right? But from the plane section remain plane, say origin normal to the section normal to the neutral axis after deformation still neutral axis. That means for this element, no shear deformation, still right angle. Okay, you know what I mean? If this is a element, if you have shear deformation, it will something like this. The angle will change. That's it. But here, for the element here, the whole section do not have shear strain. So it's not right. So how do we get the shear stress from equilibrium? Okay, so we get the shear stress from dm dx equal to V. Okay? Yeah. Okay. And we also have dV dx equal to minus qx. Okay. And Vx certainly equal to the integration minus qx dx. Is my total shear force. Okay. Yeah. Then let's see, for the rectangular beam, can we derive the shear stress? Okay, let's take a free body diagram of element. Okay. And this is a cross section at X. Okay. After we have a bending moment apply on it, this M at X. And here, this section, and this is dx. And this moment at x plus dx is my moment. Okay? Then this cross section will deform the strength distribution like this. The fiber will take tension and this compression. Okay? And this cross section will have more. Because the moment may be bigger. So this deform like this. And we take the same amount here. So the same. Okay, same. So that means this red area is the more than the one. So you can say this is caused by dm, additional moment, because this is equal to mx plus dm. So this red is substrate is strain amount by m. So this red part will be the strain additional created by dm. Okay? Yeah. And for this is a rectangular cross section. This is a half H. Okay, I just show you the rectangular. But same idea, we can study others. Okay. So this is a cross section, rectangular cross section, and this is width of the beam, B, and this is a section, H. Okay. And for a coordinate section here, this is at Z1. Z1. Okay, Z1. And the height is Z1 here. Okay. This is Z1. So I want to cut it. I want to take out this part. We take free body of this part out. Okay. So we take free body diagram. Okay, and we have stress here, the strain. Okay, and here we have this amount and plus a little bit more. Okay, CD. This is AB. Okay, A, B, C, D. And certainly there was some internal force on it. Okay, and we are shown within this area we have a shear stress tau at Z1 coordinate. Okay, and we assume this direction is into that. So this is shear stress. Inside is the X element. So when you do research, this is a way to use a differential element to derive Galvani equation. Okay? So that's why in undergrad we show the free body